All right, thank you so much, Mohammed. Since we don't have a Q&A session, we'll just move to our next speaker. Will be Professor Tianli Wang. I'll just give quite a brief introduction for Tianli. Tianli received her bachelor degree in applied chemistry in 2006 from Sichuan University under the supervision of Professor Xiaoming Feng, and her PhD in organic chemistry in 2011 from the Institute of Chemistry under the supervision of Professor Qinghua Fan, after working as a research fellow in Professor Yixin Lu's group at the National University of Singapore. And Tianli then joined Sichuan University in 2016 as a full professor. Her research group is interested in designing new chiral catalyzed chiral ligands, developing new methodologies, exploring reaction mechanism, constructing biologically active molecules. She is one of the current Science of Synthesis early career advisory board member, and also the recipient of a Team Chemistry Journal Award this year, 2023. Today, the title of her talk will be Peptide Phosphoryl salt Catalysis toward Asymmetric Synthesis. Tianli, we are ready for your talk. Please go ahead. We cannot hear you. We don't have your voice. Still no.
Hello, can you hear me now?
Yes, yes. It works now. Yes.
Okay, thank you very much for you. Yeah, so sorry, now I have to turn off my camera for seeing my slides while I'm sharing these slides with you. Okay.
So Tianli, can you go to the full screen of your slides, or you want to just keep this? Well, your slide is not the presentation mode.
You said that I showing the whole screen, right? Whole
yeah.
slide.
Do you want to put the full screen mode?
I cannot see the slides. Yeah, I need to turn off the camera, and then I can find it.
Oh, I see. Then that's right. Then just go ahead.
Okay, so sorry.
That's just technical problem, I guess.
So now, can you see the whole slide, right?
Yes, yes. Now it's perfect on my screen.
Okay. Good afternoon, or maybe good morning, everyone. Yeah, this is Tianli Wang from Sichuan University of China. First of all, thanks to SOS and the Senator and Prof. Yu for offering this opportunity to share my research group's progresses in peptide phosphoryl salt catalysis toward asymmetric synthesis. Okay, as well known, the asymmetric catalysis provides one of the most efficient and practical way to create chiral molecules. According to the catalyst differences, there are three types. They are metal catalysis, enzymatic catalysis, and organocatalysis. Among them, the organocatalysis has been developed about 20 years ago, and it has unique activation models. Yeah. Moreover, the organocatalysis also has some other features such as simple operation, mild conditions, and environmental-friendly approach, and so on. So in 2021, the Nobel Prize in Chemistry awarded to Professor Benjamin List and Professor David McMillan. They made great contributions to this area. However, currently, the organocatalysis still remains big challenges, generally including the relatively low efficiency and limited catalytical models. Yeah, the chiral phosphoryl salt catalysis is an important branch of organocatalysis. It started in the 1990s and generally went through the following three stages. In 1997, Cyril and co-workers reported the first example of phosphoryl salt catalyzed alkyl reaction. This workers marked the beginning of chiral phosphoryl catalysis. However, in the following 10 years, this area was in a state of silence until 2007. Professor Oi's group developed a new type of phosphoner salt, bringing about the reveal of this field. Then the Professor Maruka and others also developed the alkylphosphoner salt. In this period, these catalysts are always red skeletons and mostly were single functional types. In 2013, Zhao and co-workers reported the amino acid-based caryophosphoner salts. These catalysts are soft skeletons and also are bi- or multifunctional ones. In general, compared with the well-known and widely applied caryoammono salt catalysis, the progress of phosphoner catalysis is very slow. The basic reason is that compared with the nitrogen atom, the phosphorus has a bigger atomic radius, thus needing to lose ion pair as well as weak induction force. So currently, the phosphoner salt catalysis suffers from limited activation models, poor stereo controls, and lateral reaction types, and so on. So we can say the key scientific challenge is how to realize the caryophosphoner salt catalysis with high catalytic efficiency and excellent asymmetric induction, particularly where the original design of new catalyst. So on the other hand, the hydrogen bonding activation is another type of weak bond catalysis, such as peptide catalysis. As we learned, in 1998, Miller and co-workers developed the caryopropylene-derived peptide catalyst, greatly promoting the development of peptide catalysis. Of note, the peptides have special catalytic advantages. They can offer multiple regulation strategies as well as diverse activation models. So based on the advantages of peptides and the defects of quaternary phosphoner salt, our strategy is combining the phosphoner ions with caryopeptides. We want to introduce peptide chain that has special caryo microenvironment into the quaternary phosphoner salt catalyst and hope to control the direction of ion pair interaction and thus enhance the ability of ion pair activation. Moreover, the peptide chain could provide hydrogen bonding sites for cooperative activation. According to this, a new type of multifunctional caryopeptide phosphoner salt catalyst has been designed and developed by our group. This catalyst can be easily prepared via module synthesis way. Yeah, this slide shows you the typical structures of our PPS catalyst, generally including 4 types: dipeptide, tripeptide, tetrapeptide, and tetrapeptide bisphosphoner salts. These PPS catalysts have some special and important features. For the dipeptide catalyst P1, from its X-ray structure, we can find it has semi-enclosed cavity. For the tetrapeptide bisphosphoner P2, based on its X-ray structure, we can find that it has secondary spiral structure, just like the DNA. More importantly, the DFT calculated ESP also indicated that these catalysts have special electron-poor chiral cavities, which would greatly enhance the introduction ability of ion pair catalysis. Okay, during the past years, we mainly developed 2 types of synergistic catalytic systems and also developed some new reactions and novel strategies for efficient asymmetric synthesis of diverse chiral molecules. Due to the time limitation, so today I just share with you one example of asymmetric synthesis by di or tripeptide monophosphoner salt catalysis. Yeah, for one example, synthesis of chiral unbridged rings by intermolecular synergistic catalysis of PPS and Lewis acid or metal catalyst. The chiral 7, 8, and 9 membered unbridged ring systems are the most typical natural structures, and they are also widely printed in a large number of bioactive compounds and pharmaceuticals. However, currently, the catalytic asymmetric synthesis of these unbridged structures still remains great challenges. It's mainly due to the following aspects. Firstly, the synthesis of such skeletons always involves middle ring formation, which has negative reaction entropy. Secondly, these unbridged structures are commonly rigid and also have complex conformations. Moreover, these unbridged scaffolds always have multiple chiral centers, so the stereo control is very difficult. So the catalytic asymmetric synthesis of 8 and 9 membered unbridged rings has never been reported so far. Yeah. In view of this, we begin the following studies. Firstly, we synthesized the unbridged 3-to-1 rings were pulled of 5+2 cyclization reaction by employing the serial phosphoner salt as a catalyst. And also, we investigated the bioactivities of these chiral products. So in order to further improve the bioactivities of such 7-membered unbridged rings, we propose to introduce fluorinated groups onto this type of chopping skeletons. Yeah. When the fluorinated alkene was employed as reaction partner, only microaddition product can be isolated. And of note, this microaddition intermediate could not be converted into the expected 7-membered ring under the PPS conditions. After a series of control experiments, we found that the activity of the substrate is not so high for achieving this cyclization reaction. So we speculated that maybe the PPS catalyst cooperated with Lewis acid can be resolve this issue. Yeah. In particular, the Lewis acid can activate the substrate by coordination, and the PPS catalyst can control the asymmetric induction via ion pair and hydrogen bonding interactions. So with this cooperative catalytic protocol, our series of 7-membered unbridged rings with fluoro groups have been synthesized in high yield with excellent E values. And also, this reaction could be further applied in the late stage diversification of bioactive molecules. Okay, inspired by this success, we further challenged the synthesis of chiral 3-3-1 type of unbridged rings. Before our work, such chiral skeletons are mainly synthesized by total synthesis or semio-synthesis way. Okay, in response to the synthetic challenges of such 18-membered rings, we proposed a strategy of relay catalysis, in which the target could be constructed through multi-step cascade. Such cascade reaction can avoid the negative reaction entropy of middle-sized ring formation. Yeah, in particular, the PPS catalyst firstly catalyzed a cyclization reaction for providing 7-membered ring systems. Yeah, they are the K intermediate, and then such intermediate could further proceed through ring opening and FC reaction by Lewis acid catalysis, and finally constructed the expected 18-membered ring systems. In the whole reaction process, the PPS catalyst could control the inertial selectivity. Okay, after a quick optimization of Lewis acid, it was found that the BF3 was the best choice for this cascade process. The corresponding 18-membered ring product can be obtained in high yields in both stepwise and one-pole operations. Yeah, under the optimized reaction conditions, the substrate scope is also good, and a wide range of 18-membered ring systems can be prepared in high yields with high inertial and stereoactivities. So we cooperated with Prof. Yu and investigated the reaction mechanism. And finally, the DFT calculations supported our previous proposed the cascade reaction pathway under the relay catalytic systems. Okay, in addition to the 331 type of 80-membered unbridged rings, another important type of 80-membered unbridged structure is the 4-to-1 series. Both of them are widespread in biomolecules and electro products, so it's also highly desirable to develop a new and efficient catalytic asymmetric method for constructing chiral 4-to-1 ring systems. Okay, at first we directly used a 7-membered 1,3 dipolar substrate for this synthetic plan. However, the reaction could not occur because the substrate bearing a middle-sized ring has very low reactivity. So it's difficult for single PPS catalyst to promote this cascade reaction. So we proposed that metal and the PPS cooperative catalysis might be able to resolve these issues. So to our delight, the initial experimental results suggested that our working hypothesis is feasible, or was feasible. Okay. So under the optimized reaction conditions, a series of 4-to-1 type of 8-membered unbridged compound could be prepared in high yield with high serous activities. Yeah, so far we successfully prepared the 7, 8, and 9-membered unbridged rings by cooperation catalysis of PPS and the Lewis acid or metal catalyst. And also we tested the bioactivities of this chiral product and found some potential scaffolds of leading compound or chiral drugs. So to date, our PPS catalysts have been successfully applied to over 20 types of reactions. And also these studies provide the new and efficient methodologies for construction of diverse chiral molecules. In fact, more than 1,000 chiral molecules have been prepared by our lab. So I think maybe this provides a powerful molecular platform for further application studies. Yeah, finally, I sincerely thank the funding support, my collaborators, and also my students. So thank you all, and welcome to Sichuan University. Yeah, thank you, Prof. Yu.
All right, thanks to Candy for such a, firstly, the time control is perfect. Also congratulating for such a successful design. Organocatalysis has been widely applied in many organocatalytic reaction, addressing a lot of challenging synthesis in asymmetric catalysis. Since we don't have a QA session, I want to just thank you one more time for the really wonderful talk.